Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 58. So in the previous lecture, we were discussing about, I'll just give it to you as a brief recap. So in lecture 57, we were discussing about rotational and microwave spectroscopy. We were discussing about rotational, which is also synonymous with microwave spectroscopy, because molecular rotations happen in the regions of, the microwave region of the electromagnetic spectrum. Rotation, and which is synonymous with microwave spectroscopy, right? So microwave spectroscopy, which is roughly, in the region of around 1 millimeter to 30 centimeters, right, in the electromagnetic radiation. And I had told you that I had stopped the previous lecture by telling you, in fact, that rotational spectroscopy, right? I'm just writing it as ROT space SP, right? Synonymous with microwave spectroscopy, right? Is the most important. Is the most important. Is the most important technique to detect molecules in space. Okay, is the most important technique to detect molecules in space. So we'll begin this lecture by substantiating this statement. I'll explain to you why is it that rotational spectroscopy, which happens to occur in the microwave region, right? Why is that the most important technique to detect molecules in space? Now the reason is twofold. Okay, why so? So there are two major reasons. The first reason is more intuitive. Okay, right? It is the more intuitive reason, and it has been discussed in several scattered contexts in the same course. For example, you consider, I think it was either in the previous lecture or the one before it, that we discussed the notion of a rotational temperature, right? We discussed the idea of rotational temperature, and I also told you that, probably when we were discussing about the different regions of the interstellar medium, where is it that, there is going to be a lot of abundances of molecules in the molecular clouds, especially in the dense molecular clouds. And what characterizes the dense molecular cloud? What characterizes the temperature of the dense molecular cloud? Are we going to be talking about like high temperatures or low temperatures? We're talking about extremely low temperatures, right? So that is one reason. That is one reason why rotational spectroscopy is important. I'll explain the connect even better. The point is that molecules in space, right? By space, I'm in particular talking about the interstellar medium, right? Exist, okay, right? Exist under very low temperatures. We're talking about the giant molecular clouds and also the dense region of certain circumstellar envelopes. The temperature has been low, right? Because that is when the various interstellar radiation field, in other words, the UV radiations, the gamma rays, etc., they won't affect the molecules. Okay, right? So they exist in dense molecular clouds, which is characterized by a very low temperature. We're talking about temperature which is less than 50 Kelvin, or sometimes even less than 10 Kelvin too, even less than 10 kelvins too sometimes. Okay, right? So we're talking about extremely low temperature. Now, under these conditions, when the temperature is very low, what happens is that the energy, you only have sufficient energy for molecular rotations to occur. Okay, right? As a consequence of this low temperature, only molecular rotations are predominant, right? So only rotations are dominant, and therefore you can only populate the let's say the ground rotational energy level, as well as, let's say, the first few rotational higher energy levels. You may not even many times reach higher vibrational levels, right? So due to this consequence, right, at very low temperature, because only molecular rotations are dominant, consequently, it is of course that rotational spectroscopy is going to be the tool to detect molecules. And all of this happens in the microwave region, right? Which is of course, a very broad region. We're not talking about only a millimeter range or a centimeter range. We're talking about 1 millimeter all the way up to 30 centimeter range. Okay, right? So because of the low temperature, which leads to the dominance of molecular rotations, and consequently, it is a natural consequence of the low temperature, therefore, that only microwave spectroscopy, right, becomes critical to detect molecules. Is critical to detect molecules in space. So this is the intuitive reason. This is the easier reason, because you would imagine, right, that the molecules have to first exist. For that, they must be part of some giant molecular cloud, which is heavily protected and shielded from the interstellar harmful radiations, right? Harmful for the molecules. Okay. So that means the temperature has to be low. And once the temperature is low, only the rotation levels are going to be predominantly populated, and therefore it's a natural consequence that microwave spectroscopy is critical. And in accordance with this fact, of all the around, say, 300 odd molecules, we were discussing in the earlier parts of this class, right? I'm talking about, say, somewhere between like lectures 10 to 20 or something in that ballpark region. Okay. Now, we understand that of more than 300 molecules detected, okay, right? Highlighting this fact of all of about approximately 300 molecules detected in space, close to 90%, more or less, okay, right? Approximately 90 to even 95% molecules detected using only microwave spectroscopy, okay, right? Molecules detected via microwave spectroscopy. All right. So please note this point, okay? That is how dominant microwave spectroscopy is in the detection of molecules in space. So that is one reason. What is the other reason? This is the more intuitive reason, is what I told you. But there is one more absolutely unintuitive reason. Can somebody guess what it is? Well, it has to deal with what kind of radiations can we actually detect on Earth. Okay, right? Now the Earth's atmosphere, okay, the Earth's atmosphere only allows certain wavelengths, of the electromagnetic radiation to reach us, that is Earth, okay, right? To reach us. I will continue here. Now, consequently, what happens is that a lot of the higher energy radiations, for example, UV radiations, some infrared radiations also, and of course the gamma rays, etc., right, do not even reach us. Now, from an existence point of view, for a human being to exist, for life forms to exist on Earth, this is an amazing thing. This is a wonderful thing, because we are being protected from the Earth's atmosphere, right, by these from these harmful radiations. However, when it comes to detecting molecules in space, right, several high energy radiations escape us, right? So therefore, consequently, we may not be able to detect molecules in space from Earth, okay, from Earth, based on the other radiations. But the microwave radiation, right? The microwave radiation, I'll continue point B here. The microwave radiations, they present a sweet spot. So the microwave radiations, they present a sweet spot, wherein almost all radiations, right, in the magnitude of around say 1 millimeter to 30 centimeter, right? All of this reaches Earth, okay, right? Reaches Earth. So therefore, right, consequently, we can detect the molecule, detect all these signals, right? And so all the microwave radiation that is emitted by, let's say, some celestial object far away from us, because all of it reaches us, we can detect molecules using this technique of microwave spectroscopy. All right, do you understand? So the first point was something intrinsic to space. That is, the temperature is low, so therefore we could detect molecules if only a transition happened from a lower energy level to a higher energy level. Now that was taken into account in the low temperature factor, and therefore molecular rotations happen to be the perfect way. The next one is centered around Earth. Okay, it is centered around Earth, and because the Earth's atmosphere is selective to only certain wavelengths, and it's a coincidence that almost all of microwave radiation is allowed on Earth, right? We can therefore detect molecules using microwave spectroscopy. All right. So these are the two major factors which tell us that rotational spectroscopy, synonymous with microwave spectroscopy, is extremely critical, right, in the context of astrochemistry. All right. Now, I also want to highlight one more fact. Okay, you could ask me a question very naturally. It is that, okay, the problem is only on Earth's atmosphere. What if we could, go above it? Can we, escape the Earth's atmosphere and detect molecules from there? Is that even possible? Well, that is exactly what space stations across the world do, right? So as of on date, right, we have space stations corresponding to the US, Russia, and China. And India is also very soon building a space station, right? And you now see one application of a space station. Now, once you have a space station, you can detect, for example, molecules, not just based on microwave spectroscopy, but also based on other radiations also. Isn't that so cool, right? And that highlights the necessity of a space station where from, you can make your observations free from the effect of the Earth's atmosphere, okay? So this point, we shall be reiterating again when we discuss our next module on astronomical spectroscopy, how does a telescope work, etc., etc. Okay, for now, just keep it in mind. All right, so this said, I'll now move on to the next topic. It is going to be that in the previous lectures, we were talking about the rotational constant B, and then I had told you that the moment of inertia is a critical parameter, right, which is helpful in detecting molecules in space. Now we discussed the detection of diatomic molecules in particular, right? For example, with diatomic molecules, we could simplify the moment of inertia. It's a tensor quantity, right? So once we consider the principal axis only, right, there shall be 3 components from the 9 components, right? And for a diatomic molecule in particular, or any linear molecule in general, right, we should only be having one moment of inertia value to worry about, okay? But in the case of polyatomic molecule, the scenario changes. I'll explain to you, okay, right, the interesting features, okay, the interesting features of microwave spectroscopy for polyatomic molecules, and tell you why it is important in the context of astrochemistry, okay? So the next idea is going to be interesting aspects of microwave wave spectroscopy for polyatomic. We're talking about, any species which contains more than 2 atoms, that is n greater than 2 molecules. Okay. Now, recall that for diatomic molecules, I just said that the moment of inertia, right? The moment of inertia at tensor, right? For a diatomic molecule and it has 9 components, and even if you consider the principal axis only, the 9 components, right, get reduced to one single value. Now that is due to the symmetry of the molecule, right? And then the moment of inertia along the 2 perpendicular axes, it has the same value. Okay, right? But in the case of polyatomic molecules, what happens is that now in the case of polyatomic molecules, now this reduction to one specific value of I does not happen. Okay, due to the lack of symmetry in the molecule. Consequently, now recall that for a diatomic molecule, for diatomics, and in fact more generally for any linear molecule also, we say that the energy of rotation from the rigid rotor model is given by h bar square by 2I, where this I is one unique value. Okay, we're not talking about different components, right? We're talking about one unique value. Okay, right? This is for diatomic molecule. But for polyatomic molecules, and this is given by B times J plus 1, where your B is the rotational constant, which can be expressed in terms of h bar and other constants, right? And the condition from quantization is that your J can be having values of 1, 2, 3, etc. Correct? Okay, right? Your J can be having all the values starting from 1, 2, 3, etc. Are we good, right? This is what we saw in the previous lecture. Okay, right? Now, but all of this was possible. We of course did not do the complete derivation, right? J could also be 0, in fact. Thanks for pointing that out. J could also be 0. Okay, right? J could be 0 also. But the point is, your all of this expression could be derived because we had one value of I, right? Only one particular value of I. But when let's only consider the principal axis, okay, right? So when I along the principal axis, right, can have more values, then your E rotation is going to be expressed as h bar square by, let's say, 2ix plus h bar square by 2iy and h bar square by 2iz, right? In general, instead of having one term in the energy expression, we're now going to be having 3 terms, right? So there are going to be therefore more complications introduced. Okay, what exact complications? Now, what exact complications are we talking about? Now see, I was telling you that this particular term J, right, it is called as a quantum number, right? I had introduced this term J. It was called as a quantum number. Now, for one energy expression, corresponding to one energy expression, we had one quantum number, J, correct? This is called as the rotational quantum number. Okay. Now, therefore, as we extend the terms in the energy expressions, right? So corresponding to Ix, Iy, and Iz, right? We shall be dealing with, I'll write it here, due to 3 terms, 3 independent terms in the energy expression, right? In E rotation for the polyatomic molecules, right? Due to that, the number of quantum numbers, right, which was only 1 in the case of a diatomic molecule, is going to be 3. Okay, right? The number of quantum numbers is greater than 1. Sometimes, depending on the symmetry of the molecule, your Iy and Iz can be the same, etc., etc. We will look at those examples in a tutorial, okay? But for now, more generally, we have like 3 different values of the moments of inertia, and they result in not just one quantum number. We call that each quantum number arises from one particular term in this expression, okay, right? Now, because we have 3 terms, each of which is independent, I mean, of course, h bar square is common, and if we factor this h bar square 2 out, the Ix, Iy, and Iz are as such independent of one another, okay? So therefore, right, the number of quantum numbers is greater than 1, which implies that, recall again the diatomic case wherein, we were discussing the rotational spectrum. We were talking about the p branch, the r branch, etc., right? So we shall be having more features in the rotational spectrum. What sort of a feature I'm talking about? Well, for diatomics, we had, corresponding to delta J equals 1 plus 1, we had the R branch, and delta J equals minus 1, we had the P branch, correct? If you recall. Now that was all expressed in terms of the J quantum number. But here, on top of the J quantum number, we're going to have like at least 2 more quantum numbers, right? So because the number of quantum numbers is going to be there, is going to be more, right? The number of lines in the spectra are also going to be increasing. In other words, to forget, like analyzing a signal obtained from space, even on Earth, okay, right? Even on Earth, to precisely demarcate each line and to assign it to a specific transition is going to be very hard, okay? So we'll be having much more features in the rotational spectroscopy, which again implies that assigning the rotational spectroscopy, right? Assigning the spectrum obtained, the rotational spectrum obtained of any polyatomic molecule to any one molecule. In other words, mapping a spectrum to any one molecule is not so easy as it was in the case of diatomic molecules. And recall, on top of that, there are also going to be some isotopic distributions abound, okay, right? So assigning spectrum to a molecule is harder relative to what it is for polyatomic molecules. So please get this point clearly, okay? It is hard not just for the signals that we obtain from space. It is hard even for the spectra that we get on Earth itself, okay? So there are more complications, and this in fact explains why, if you take a look at the list of molecules, for example, from the Cologne database for molecular spectroscopy of molecules in space, right? The smaller molecules, that is, molecules containing 2 or 3 atoms or 4 atoms, were discovered much earlier. And it is only now, we're talking about the 2020s, not even in the decades before that, that molecules containing more than 5 or 6 atoms, for example, glycoaldehyde, we're talking about something like benzonitrile, etc., etc. Some of those larger molecules are getting detected only more recently. Why is it? Because we have an improvement in the instrumentation corresponding to microwave spectroscopy. As a result, our resolution is getting better and better. Okay, so this is an intrinsic challenge in detecting polyatomic molecules in space. The fact that there are going to be more complications as a result of the moments of inertia, right? Not just funneling down, and becoming just one value as we saw in the case of diatomics. So please understand this, okay? So these were 2 aspects of rotational spectroscopy that I wanted to share with you all in today's lecture. With this, I hope I have impressed you folks enough that rotational and microwave spectroscopy are exceedingly critical. There, of course, there is no end to me going on about the details of each and every single spectrum. In a tutorial, I shall discuss some specific spectra of molecules and how from them, we get the various parameters such as bond length and how the structure of a molecule could be determined, etc. Okay, but please understand that microwave spectrum and rotational spectrum are extremely important to understand and detect molecules in space. All right. On that note, we shall now move on to vibrational spectroscopy, which is another interesting aspect via which molecules could be detected in space. Okay. Now, we're now going to be discussing the spectroscopy corresponding to molecular vibrations. Okay, so I think we've already discussed in the beginning portion of this lecture, of this class, that molecular vibrations are equally important too, right? Now, recall, when we were discussing about the simplified version of a potential energy surface, right? Especially the ground state, we were discussing about some system like this, right? Where this is the potential energy of the system, and then this is the internuclear distance. Let's consider a simple diatomic to begin with, okay, right? Let's say something like H2. Now, if we consider this system, we saw that the potential energy curve, right, is going to be something like this, right? And this region corresponds to what is called as the equilibrium bond length. We're going to use the symbol Re, right? R sub E, right, to denote equilibrium bond length. So now, this is kind of the model. This is kind of the model we are going to be using to describe molecular vibrations. Now, look at the shape of this curve. Okay, if you look at the shape of this curve, right, in the vicinity of this region, Re, right, I will just put it in a box. This region alone, right? In this region alone, right? You kind of note that the shape resembles a parabola, correct? It resembles the form, the curve y equals x square. Of course, with the origin being shifted. I'm not specifying what the origin is for this curve intentionally, okay, right? So it's of the form y equals x square, right? So closer to the equilibrium geometry, right? The shape of the curve, right? The shape of the potential energy surface, right, resembles a parabola. What I've written here is parabola, P-A-R-A-B-O-L-A, in case the handwriting is not clear, and especially because it's written in the bottom part. Okay, so this region here of the molecular reduced version of the potential energy surface, right, it resembles a parabola close enough to the equilibrium bond length. It's of course not valid as we go further, as the molecule dissociates, or as we squeeze in two nuclei together. In this region especially, it is a very safe and a sound assumption to believe that the shape of the PES is a parabola. Okay, right? So I will end this lecture on this note, okay, and I will continue with vibrational spectroscopy and more aspects of it in the next lecture. So to sum up what we saw in this class, I started off by explaining to you and substantiating the statement I made towards the end of lecture 57. That is, why is it that microwave spectroscopy is exceptionally important and in fact the most important technique to detect molecules in space? We gave two reasons. One was the intuitive one, that the temperature in the interstellar medium where molecules could be detected is very low. So therefore, only the rotational energies could be populated, and consequently microwave spectroscopy becomes extremely important. That is one point. And atop that, because we are observing from Earth, right? Earth, what is called as the opacity of Earth, right? Now that allows for the entire region of the microwave radiation, right, to enter Earth. So therefore, that's a very facile technique for us to detect molecules in space. So we saw that. And after that, I was telling you about the complications in polyatomic molecules, in the microwave spectra of polyatomic molecules arising due to multiple values of moments of inertia. So that leads to interesting features, and that is why it's only now that we are detecting polyatomic molecules. And lastly, I just started off with an introduction to vibrational spectroscopy and pointed out to you that the region close to the equilibrium bond length resembles a parabola. On that note, I end this lecture and see you all in the next lecture. Thank you so much.